Good morning, everybody. Thank you. We got a lot to do, right? Okay. And so let's jump in and give you some context really quick. We've been doing these toolboxes. It's his, isn't it? Or was it yours? That was mine. Okay. I thought it said Ishan on the back, but all right. So these are all the toolboxes we've done, right? And we're going to do a new one when we finally get to chapter 10. But that is next unit, right? That's not this unit. So what we're about to do in chapters 8 and 9 is do these all over again. So today is kinematics. Okay, we're just going to study kinematics from chapter 8. Chapter 9's pretty big, and that we're going to do the other 3 in one chapter. That's both good and bad, but your textbook author could have paced this probably a little bit better. But we're going to tackle kinematics. Now, we've done circles before. We've kind of hinted at it. We did like a vertical circle with forces. We did centripetal acceleration, all that kind of stuff. All of those cases, our circular motion was constant in the sense that it never sped up or slowed down. But now we want to be able to handle not just the center-seeking acceleration that's there when something goes in a circle, but what happens if a tire speeds up and slows down, or the merry-go-round, or whatever things are going in circles. Just about everything moves in circles at some point. So that's what we're doing. Okay, so let's see here. Does anybody remember the toolbox from way back, like in chapter 2? Oh, yeah, okay, right. So I'm just going to, these are the linear versions, right? Let's see, was one of them that? Yeah, okay. And then, was it that one? Yeah, I think so. And then this is me not looking at my notes. You got probably not deltas on the ones we did back then, but the delta just means right final minus initial. Okay. Do those look like old friends? Yes. They kind of do, right? After the last unit, and now you guys thought that was hard. I remember that, right? The first unit is it's class, right? But now it's kind of like coming home, isn't it? Right? It's not Newton's laws, which is a good thing. Okay, so in order to be able to use this toolbox, we had to be able to understand what like position meant and displacement. We had to understand velocity and how it was different from acceleration. And I know for many of us in this room, you're still trying to work out the difference between velocity and acceleration. It's one of those things that takes time. And we did all that in the context of something moving in a straight line, or maybe rolling down a hill or something like that. Well, now we've got to do the same thing, but in circles, right? And I hate to break it to you, but X and Y just aren't, the Cartesian coordinates aren't the best thing to be able to talk about how this wheel is rotating, okay? So those of you that have had enough math, where do you think we might need to go? There's a special coordinate system that you probably struck fear into your hearts when you first learned about it. Polar coordinates. Kind of a funny name because it hasn't done anything to do with polar bears, right? Okay. But polar coordinates are the coordinate system of rotation. So let's dust off just a little bit of symbols and ways that we reference what we're talking about, and then we'll get back to the kinematic equations. That's a circle. I love being able to cheat like that. Okay, and we're gonna liken this, right? We're still like Cartesian coordinate system's still there, but if I want to know, say, where that point is on the circle, does anybody remember what 2 things we needed to know? That's a 45-degree angle. Sure. Okay, good. we needed to know like the angle. I'm not going to put 45. I'm just going to put theta because it can be anywhere around the circle, right? Okay. But to know that point, theta wasn't enough. What else did we need? Good. Okay. So instead of x and y, we use r and theta. When it came to distance, like how far this point on the circle moved, I like to think of like a bug sitting on the edge of the tire or something, right, as it rolls around or something. Like how far, like what was this distance right here? Anybody remember that? It's arc length, okay? So the symbol for arc length generally used is S. It just means like a generic distance. And the arc length, what units does arc length have? No, it's a length. So it has units of meters, doesn't it? Okay. What are the units of radius? It's meters, right? So if we already have a meter over here, and we already have a meter over here, we really don't need anything else, right? Wrong. Because the arc length is not the radius, is it? The arc length equation is the radius times the angle that it goes through. But a meter times a degree doesn't make any sense. So what units are we going to use for theta? Radians. Don't raise your hand, but how many of us are still confused about what mode our calculator should be in? Right? Am I right? Okay. How do you know when your calculator should be in degrees mode? If your angles have units of degrees, right? Sine, cosine of 78 degrees, right? It's right there. So when should your calculator be in radians mode? When there's no degrees. When there's like pi over 2 or pi over 4, or even more importantly, when you don't know and aren't certain. What do I mean by that? What unit must this angle have in order for the arc length to come out as a length, seeing that we already have a radius that already has units of meters? It needs to have no units. And the way that angles have no units is by measuring them in radians. I'm sorry, I'm not responsible for this. Okay? What the heck is going on here? Let me go on a little bit of a mathematical rant here. It's important. Okay? This isn't a tangent, this is a rant. Okay? Can anybody tell me what pi is? That's the number, which is an approximation. What is it? A what? No. What is it? Math education in this country is just, oh. You were probably taught this and then they just completely buffaloed you with 3.14159, blah, 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 right? Okay? It's the ratio of the circumference of a circle to its diameter. And you're like, so? What are the units of circumference? Meters, distance, right? Okay, because you're going all the way around a circle. What are the units of the diameter? Also meters. What's a meter divided by a meter?
1.
Nothing. Right? Pi, what are the units of pi? Yeah, but when we say an angle of pi over 2, what do we always say? Pi over 2 radians, which is equivalent to 90 degrees. What's a radian? It's a unitless unit. It's a label. It's a lie. The radian is what we throw in there because our human brains want to attach something to a measurement, right? But the radian has no dimensions to it. It's literally something that we came up with because meter over meter didn't sound good. So we do have to work in radians, and importantly, I will not be responsible for your calculator being in the wrong mode when you go do your math class or your chemistry class or whatever, right? From here on out, you got to remember to check the mode, right? Some people come up to me, Mr. Bale, my calculator's lying to me. And I'm like, okay, are you in degrees or radians? Like my first question. It's a problem. How do we get between degrees and radians? There's 180 degrees in pi radians. Okay? So there's your conversion factor for you. And we will have to kind of go back and forth depending on what they tell us. But yeah, radians is a unit that has no units. I wish I could fix it for you, but I can't. Okay, so with arc length defined for us, okay, we can start talking about position, velocity, and acceleration. The position, right, for anything on this wheel, right, is going to be given really by what thing. Think about arc length and think about the thing that's changing. Yes, I reference this position with both r and theta, but if I'm going to talk about circular motion and this thing moving in a circle, what's the thing that changed? Was it r or was it theta? It's theta that does the changing, right? So theta, our position along this circle, right? One way to think of it, you could find it by doing that. But more importantly, right, theta feels an awful lot like the thing that's changing over here in our kinematics, right? Okay, we're going from one thing to another. We're going from one place to another. And for something that's moving in a circle, that's not the radius that changes, it's the angle that changes. Okay, if that's true, and here, let's make another list right here. We'll go circular and linear, right? So linear would have been delta x or delta y, right? Either of those. Here, it's that theta, and I love writing delta theta, right? Just because it tells me that something's moved and changed. Okay, what was velocity? Remember the basic definition of velocity? Yeah. No, direction. It was, yeah, okay, it had units of meters per second. So it was that distance traveled divided by time, right? Technically a delta time, because there's beginning and ending time. Okay, so what is the angular version of this? Right? We need to be changing something in time. What's changing? The angle is changing in time. So, angular velocity and angular speed will be a change in angle over time. What unit would that be? A radian per second. Sorry. Okay. And now we need a symbol for it. We need a way to symbolically represent what this thing is. In linear terms, we used v for velocity. What are we going to use for angular velocity? Okay, I heard it correctly and I heard it wrong. Okay, that right there is an omega. Among the other things you'll be learning in this class is the Greek alphabet. Okay? This is an omega. This is a W. What's the difference? One's pokey, right? Okay. In the past, this wasn't a bad thing to do, I would throw chalk. You know those little tiny bits of chalk that would be in every tray, right, on any chalkboard, right? I would find the littlest leftover pieces of chalk, and when somebody said W, I'd walk over, I'd grab one, and I'd throw it at them. Okay? As a reminder that that's not a W, it's an omega. This became problematic when we switched to whiteboards and whiteboard pens because these hurt. Right? No. Okay? Because now I can get sued. Right? So, yeah, just be careful around me if you start saying W when it's not a W. It's an omega. All right. What happens when you change the velocity in time? What do we call that? Call that acceleration. You want to give a guess as to what we're going to change over here to get angular acceleration? Yeah, we're going to change omega in time. If only there were a Greek letter that looked like an A. Oh! Alpha. Okay. So,
is that a D?
It's an alpha.
No, the T.
Delta T. It's supposed to be a triangle. I was getting excited and started going too fast. Yeah, technically these are all derivatives, but I'm not allowed to write that. So what's going on here? Is angular velocity really any different from linear velocity? It's Greek, right? So it's gone to a toga party. That's really all it's done, right? It's still the same idea. We're still changing something in time, right? And then acceleration, right? Acceleration was this change in speed. It was speeding up or slowing down the velocity. And that's really no different when it's talking about a circle. This wheel has omega. Why does this wheel have omega right now? Because it's spinning, right? Because it's going someplace angularly, right? There was too many lees in that one. Does it have alpha right now? Yeah, why? It's slowed down. Is it going to have alpha while I speed it up? Yes, right? Speeding up, slowing down, that's still acceleration, right? The speed that it's going, that's still velocity. Where we are is the position. These are the same ideas, we've just given them a different coat of paint. And it can throw you. Like when you're first exposed to this, it feels weird, it feels different, feels unique, but it really isn't. The basic fundamental ideas for velocity doesn't matter if it's going in a line or going in a circle, conceptually. In practice, we do need to be a little bit careful about how we write them down mathematically. So, if I've got the linear and the circular kind, right, okay, I'm gonna go ahead and write down the new toolbox. Now, I could spend the next 40 minutes deriving for you how to get to this new toolbox, or I can just tell you what it is, and I'm going to do the second choice, right? Because you guys don't need to know where they come from. You guys need to know how to use them, right? And when it's appropriate to use them, and that's what I want to focus on. So, just like over here, right, our new ideas, they're the same old ideas with a fresh coat of paint. Like I said, they went to a toga. Does anybody know what a toga party is? No. It's kind of an old thing. It's where you go to a party wearing a toga, because old Greek people wore togas, right? Okay. It's a college thing. You may or may not get exposed to it, right? So, at least it'll happen every once in a while. So we're just going to put a new coat of paint on here. So work with me, right? Instead of V, let's do the first equation. Instead of V, what's it going to be? Omega. And then instead of V naught, it's going to be omega naught. And what does omega naught mean? The initial angular velocity, right? And omega means final angular velocity. Final and initial. Instead of A, it's going to be alpha, and instead of T, it's going to be T. There's no angular. Yeah. All right. Instead of X or delta X, it's going to be delta theta. I'm starting to write these with deltas now. Your book continues to just write theta equals. I kind of like the delta just because I don't always assume I start at 0. All right, V naught becomes omega naught T plus 1/2 alpha T squared. And then omega final squared equals omega naught squared plus 2 alpha delta theta. Are these new equations? No, they're not. They're the same equations we had back in chapter 2 with different symbols in them. But the relationship, the problem-solving method, everything else stays the same. It doesn't matter that we're in a different coordinate system. And I know you're sitting there going, yes, Mr. Balogh, it matters. I get you. I understand why your brain's thinking that. But if you can come to a place where you can accept that you've done this before, it's going to be a lot easier for you. We're going to fall back on the old ways, right? Which are good ways. There are a couple extra things we need to add to this toolbox. So I've already written down one of them. It's the arc length, right? It's the way to kind of figure out distances when you know angles. And then there's a few here I want to give you. So in our linear case, we did, do you remember this equation? The centripetal acceleration equation? Didn't I ask a question on the exam for you to just calculate this? Or no, solve for the radius, and several of you forgot how to do math all of a sudden on that problem, right? So yeah, division can be really hard when you're doing a bunch of other things. So so what do you do if you're talking to somebody and they don't know your language? And you don't know their language? Right? Google Translate, right? Okay. Or any other, like Google for the Android phones, there's a translation app built into iOS for the Apple phones, right? Google, but I'll just call it Google Translate, right? You can use Google Translate. Now you can do it in real time. Don't several new AirPods or AirBuds or whatever, don't they just do it in real time in your ear while you're talking to somebody, right? Like I kind of think we've got the communication problem solved in terms of languages, right? We still can't communicate with each other because we're all stupid Americans, but that's a different issue, right? So what are the Google Translate codes for getting between linear and angular terms? Velocity is equal to radius times angular velocity. Centripetal acceleration turns out to be r omega squared. And then we're going to pick up a new one called the tangential acceleration, which is equal to r alpha. That right there in the red box is the toolbox for angular kinematics, with the added little sprinkles of being able to go back and forth between the linear toolbox and the angular toolbox whenever you need to. Yeah, okay, good questions, right? You notice I threw some little T's on VT and AT, right? Okay. What's AC? Centripetal acceleration. So remember, there's an acceleration that points towards the center anytime an object is going in a circle. We've talked about that before. But centripetal accelerations do not account for speeding up and slowing down the omegas. In order for omega to change, there has to be a tangential push, right? Okay, so this is omega with it just spinning, right? But if I make it go faster, that's an alpha, isn't it? But that alpha was related to a tangential A. I had to grab the wheel and I had to move it, right? Perpendicular to the radius tangentially, right? Okay. There's also a tangential velocity. So as this wheel goes around, this top piece of the wheel, it's moving, depending on which way it's rolling, right? But it's moving tangential to the circle. So if I rotate my wheel like this, right? This point right here, up or down? It's going up, right? Left or right? Left. Up or down? Down. Left or right? Get the idea? Okay. So there's these, at any point I can just grab a piece of this wheel and I can give you the tangential velocity that it has. Same thing for, say, moving my tennis ball around on the end of a string, right? It's going in a circle, but at any instant we could cut that string and it would move tangentially to the circle. So Vt is the tangential velocity. We're just really trying to underscore, right, that, yeah, omega is something in rotation. The velocity it has at that instant will be tangential to the circular path. Same thing goes for the tangential acceleration. Tangential acceleration is what causes alpha. Centripetal acceleration is there because the object's moving in a circle. So speeding up and slowing down a tire, is that AC or is that AT? It's AT. The centripetal is there just because it's a circular motion. But the tangential ones are the ones that cause speeding up and slowing down of the motion. And like I said, they're Google Translate. They allow us to go back and forth. Okay, let's discuss a different problem. This is one's going to come back later, okay? Which way is this wheel rotating for you? How do we describe this rotation? Counterclockwise. Some people like to use anti-clockwise. Sure, why not? Okay. But it doesn't look that way for me. No, this is clockwise. This is the problem, right? And we don't use clocks anymore. Okay? Right? Okay? So, that is a clockwise spin, the way that clock hands would rotate if everybody was old. Right? Okay? This is counterclockwise, but the problem is clockwise and counterclockwise depend on which way you're looking at it. This is counterclockwise for you, but it's clockwise for me. Do you see the problem? Okay? So, physicists have overcome this problem with something called the right-hand rule. Everybody raise your right hand. Repeat after me. I solemnly swear that I'm... No, we're not going to do that. Put your hands down. I just needed to make sure you all knew which ones were your rights. Okay? Have I quoted you the preeminent philosopher of our age? No. This doesn't sound familiar? Okay, that was Physics 2B. The arguably greatest philosopher of the modern era, his name is Winnie the Pooh, had this to say, okay, about telling your right hand from your left hand. Think about this for just a second. I have no trouble telling my right paw from my left. It's knowing which one to start with that makes all the difference. This is deep. This is very deep. You think about that one for a while, you're going to go places, okay? Right? So I don't know what you need to do. I have dyslexia, so this is impossible for me, right? But put Post-it notes, tattoos, something, right? Because I've watched students in the midst of physics problems, they're so stressed out, you forget which one is your left and right hand. I just watch it happen, okay? So that's why I wanted everybody to raise their right hand. I needed to make sure that you all knew, okay? So good job, you passed kindergarten. take your hand, your hand, right, it's got a thumb, and then it's got these 4 fingers. You're going to wrap your fingers around in the direction that the wheel is spinning. So in this case, I take my fingers and wrap them around like this, and notice which way my thumb points. Towards you guys, right? And it doesn't matter which side I do this from of the wheel. Either side, and I get exactly the same direction with my thumb. So the direction for angular velocity is given by a right-hand rule, and it points basically along the axis of rotation. We generally will just fall back on clockwise and counterclockwise, because when we're drawing on a piece of paper, everybody's looking at the paper from the same side, we hope, right? So that's not so much of a problem, but just realize it's actually a solved problem in physics, because, again, do this one. Which way would you guys wrap your fingers around? And your thumb ends up pointing which way? This way. And it's exactly the same thing for me on this side of the wheel, right? My fingers wrap in the direction the wheel's spinning, and my thumb ends up pointing the same direction. Which way is your thumb pointing now? Which way is it rotating? Around like this, and your thumb is now pointing down, right? Which way is it pointing now? Up, right? No matter which way I orient this circle in space, there's a unique direction for that vector, okay? And the reason I showed you that right now is not because we're actually going to use it right now, but there are more right-hand rules coming up that we're going to have to use for things like torque. And so I want you to kind of be used to this idea of a right-hand rule, so that the next time I teach you, when it's more important, why am I putting that there? It's the second time your brain is seeing it, okay? This is the first time. We're now going to kind of ignore it, and we're just going to do some kinematics. I wrote down I got the toolbox here, okay? And so let's do a problem. True story. I used to work for Seagate way back in my freshman and sophomore years of college. Seagate employed me in their, oh my gosh, what was it called? It was pre-sales technical support. We got phone calls from people who had not yet bought a hard drive and needed technical support. Okay? Since this was back in the age of the dinosaurs, the early 90s. Yeah. Okay. Hard drives, so like the concept of a server farm had not yet really occurred. We had mainframes and stuff like that, and they often needed lots of storage. And so like we would get calls from big companies saying, we need to, replace drives in our mainframe. What drives are compatible with, say, our controllers and our mainframes? It was actually pretty complicated back in the day. Nowadays, get the right form factor and you can pretty much nail it. And there's only there's about one way of connecting a hard drive now. But back in the day, there were lots of different ways. You could do parallel, you could do series, you could do all kinds of stuff. And so we'd have to work with the customers to tell them what to buy. This is not corporate secrets. I took data from hard drives, right, and to make this problem, okay? So I've got a picture of a hard drive down here, right? And a hard drive functions by spinning, right, the data disks underneath this read-write head that's sitting right here, okay? That read-write head moves in and out in a line, but the disks go around in a circle. Your generation doesn't have to suffer from this too much anymore. But it used to be when you turned on a computer, you kind of had to wait. And you were waiting for the hard drives to wake up. If it came back from sleep, okay, you'd hear this ka-chink, kunk, as the hard drives went from their parked and safe positions to spinning up to the speed that they had to be working at in order to read data on and off of the drives. Nowadays with solid state drives and things like that, there's no time. There is time because Windows, but anyway. So we've been given data, right, on the spindle speed, okay, of a certain hard drive. This is actually a fairly common spindle speed for a hard drive. They do come in different values. 4200 is not common very much. 54 is pretty common still. 7200 RPM, 10,000 RPM, 15,000 RPM. The faster the spindle speed, the higher performance of the drive, but the less time it lives or is able to store good data on it. But 7200 is a good thing. And hard drives are still like everything that's on the internet is basically on a hard drive. Information is cached or temporarily held in solid state, but longer term storage and cheap longer term storage still happens on hard drives and, believe it or not, tape drives. Kind of modern versions of those old 1960s tape reels. Those are still used for long-term backup. So anyway, I'm a nerd. 7200 RPM. What's an RPM? It's a rotation per minute, right? Is that anything close to a standard unit in our rotation stuff? We sort of talked about the units here, right? This is a radian per second. What's the acceleration? Radian per second squared, right? Radians per second squared. Those would all be like the standard units for angular things, right? So a revolution per minute is definitely not that. So we're going to have to fix that. 30 revolutions per second squared. What is this number? Is it a position, a velocity, or an acceleration? How do you know it's acceleration? Second squared. Look at what you guys know. This is great, right? You learned something. I learned you something. I is a college graduate. Okay. What do we do? What did we do way back when a car was accelerating from 0 to 10 meters per second? Drew a picture. We visualized, didn't we? Drew a picture, made a list. Do you remember the list? Good old days of the list when you didn't have to draw a free body diagram, right? Okay. Do you remember what the list had in it?
Velocity, initial, acceleration, time.
Good. Okay. Where did all those things come from? They came directly from the toolbox, didn't they? We just march across the toolbox, picking out every symbol and every term. Omega, omega naught, alpha, T, theta. Are there any more symbols? Not really. I mean, we could do the linear ones, V and X and T, right? But like, we're doing angular kinematics now, aren't we? Okay. So this is the total list of things we could know and not know. Do we know how fast the hard drive platters are going after it starts up? 7,200 RPM, right? Do we know how fast it started at? 0. Do we know the acceleration of the disks? Yeah, 30 revolutions per second squared. Do we know how long it took? No. Do we know how far around, how many radians the platters turned through? No. What are we looking for? Time in this first part. Let's just do the first part, right? Okay. We do need to convert some units. We'll do that, okay? But let's strategize real quick. How are we going to get time if we know omega, omega naught, alpha, and T? Turn to your neighbor, tell them which toolbox equation you're going to use. Go. All right. Did everybody say the first one? No? Why not? You want to use the third instead? What's wrong with using the third one? Doesn't have time in it. And we don't know the theta, right? What's wrong with the second one? Don't have time, and that's quadratic, and we don't have theta. So the first one, this first one right here, the only thing in that equation we don't know is time, right? So what's the strategy? We're going to use the first equation and solve it for time. Are any of you still writing down your strategy? No? Too much writing? This is an English class. Those of you that still are know how powerful it is. Okay. That's what we're going to do, but I guess we could do it right now. There, I did algebra. Okay. But before I go and chuck numbers into that equation, the numbers are wrong, aren't they? They're not in standard units. And standard units is how we stay safe. So we got to convert these into standard units. How do we go from RPM to radians per second? Yeah, but when Google's not available, you have to do it on an exam. Or you're stranded on a deserted island for some reason, you're doing angular kinematics. I had a teacher that collected our notebooks and graded our notes. He was my junior level mechanics teacher. Good man, strange in the head. And when we asked, why are you grading our notes? He said, I want to make sure that if you are ever stranded on a deserted island and you had to recreate physics from scratch, your notebook would contain everything that you would need.
But what if we don't have the notebook?
I raised my hand and I said, Dr. So-and-so, Dr. Mason, if I'm stranded on a deserted island with my physics notebook, it will be used to start a fire to get off that island. He didn't give me a very good grade. All right, so 7,200 revolutions every minute. What are we going to do? We're going to go back to chapter 1. We're going to leave enough room to do it. Chapter 1. Do you want to do the minutes or the revolutions first? Revolutions? For every one revolution, how many meters are there? The circumference of a circle, right? Every time you go around a circle once, you go 2 pi r meters. 2 doesn't have any units. Pi doesn't have any units, radians, but r does, units of meters, right? So one revolution is 2 pi r meters. Okay, we took care of the revolutions. How do we take care of the minutes?
1 minute is 60 seconds.
60 seconds in a minute. There you go. Okay, so the minutes cancel, and I'm left with meters per second. Sort of a shortcut for this is you can get rid of this 2 and then turn this into 30. So basically multiply by pi over 30, right? If you want the short version. But yeah, that'll get us a number. Did I get the right note? 754 radians. What did I do? Hold on a sec. Wait. I didn't want to go to meters per second. What the heck am I doing? 2 pi, I'm an idiot. 2 pi radians, there we go, Now my units are working. How did I know my units were wrong? What do I need? I need a radian per second. Sorry about that. See, even I can make mistakes. That one was not intentional. That was just being stupid. Okay, a radian per second is what I wanted. But I knew how to fix it. And it's still, you can still get rid of the 2. So it's just pi over 30. All right, no r involved. I went too far. Okay, 754 radians per second is what I got. Somebody can check me on that because I obviously have already made mistakes. 240? 7,200 times 3 divided by 30 is 240. There's pi in there, 3.14. Okay. All right, so this is equal to 754 radians per second. And then the other one, the alpha, I've got to convert over, right, is 30 revolutions per second squared. Okay, which of those two things do I need to fix? The revolutions, right? The second squared is okay. I just need this in radians per second squared. So 1 revolution, 2 pi radians. There we go. Revolutions will cancel, and I'll get a radian per second squared. When I did this, I got 188.5. So I'll put that over here in my list. Radians per second squared. All right. And now I can come up here and do my time. My time is going to be omega, which is 754 minus 0 for the initial, all divided by 188.5. That gets me a time, lo and behold, 4 seconds. Take this drive 4 seconds for the motor to get up to the speed before it could even start reading and writing information. Actually, a little bit longer than 4 seconds because that's the spindle speed. The drive still needs to run calibration routines before it can start read-write operations, which takes another half second or so. All right. There used to be an option in the control panel for various operating systems and operating system flags where you could tell the computer to sleep but not turn off the drive. So like everything else was asleep and not doing something, but the drives were still spinning so that when you woke it back up, there was no lag time, right, for the hard drives to come spinning back up again. All right, we found the startup time. Okay, now what are they talking about? This second part here. Okay, on this hard drive, the area where the data existed kind of started right there and then went almost out to the very edge of the drive. And so what I've given are the 2 radiuses. What's the first one? 1.5, and then the 4 centimeter one out here. Okay, so the data, right, exists sort of in this portion of the disk that starts at 1.5 centimeters and goes out to 4 centimeters. And they want to know how fast the platter is moving at those 2 different radiuses. Well, this is kind of a funny question because what is omega at the inner radius? Drive's already spun up, it's at full speed. What's the angular velocity? 754 radians per second, or 7,200 RPM. What is it at the outside edge? The same, right? The platter is going through the same angle in the same amount of time, right? Like if we look at a wheel, right? Is there any difference in the amount of angle down here near the axle compared to out here? No. But what is different? The radius. And so therefore, the tangential speed. Where do you ride? Which horsey do you go for on the merry-go-round? The inner horsies or the outer horsies? Neither, Mr. Balogh. I go for the pretty horsey. Which is the one everybody's always racing for?
I don't know.
The outer ones. Why the outer ones? Whee! If you get motion sick, go to the inner ones. Why are the outer ones the more whee factor? They go faster. Their tangential velocities are bigger. They have to be. They're at a bigger radius, right? So to get the same angle, they have to be moving faster out there in the same amount of time. So this question isn't so much asking us what's the angular velocity. It's asking us, it says how fast. And you could answer, well, 754 radians per second. That's boring. Let's find the velocity at 1.5 centimeters. This is the tangential velocity, the speed at which the platter moves underneath the read-write head. If we go to the toolbox, we'll find out that we can Google Translate between linear tangential values and their angular counterparts. This is the Google Translate for this one. So what are we going to put in for the radius? No, we're going to put in 0.015. Why? Take the centimeters, put it in meters. Standard units are safe. Anything else is a guess, kind of. What are we going to put in for omega? 754 radians per second, right? So there's a meter right there. What's a meter radian per second? Remember, a radian is nothing. It's not a unit, right? It's a placeholder. So what's a meter radian per second? It's a meter per second, which is a velocity, isn't it? Okay. So if I do that, I get 11.3 meters per second, or about 25 miles an hour. At 4 centimeters, what am I going to put in for the distance, the radius? 0.04 meters times 754 radians per second. That one gets me 30.2 meters per second, or approximately 68 miles an hour. So data on the surface of the drive is traveling anywhere from 25 miles an hour to 68 miles an hour, depending on where it's been stored, which radius it's been stored at. That's important for computer performance. If you need to get information in and out quickly, where do you want the information to be stored? On the inside or outside? On the outside. You're reading more information per time on the outer edge of the drive. On the inner edge of the drive, you put data that isn't accessed very often. You want your read-write head to be way out there at the edge where things are happening the fastest. Fastest hard drive speeds ever recorded in the lab was I think it was a 54,000 RPM drive. The problem is that if you get too fast, the platters break themselves. They shatter under the speed. And for the little while, engineers couldn't figure out what was going on because they had what they were doing is that they were breaking the speed of sound with the outer edge of the drive platters. And so they would break the sound barrier on the outer edge, but not the inner edge, and it would set up a wobble and it would destroy the drive. Chapter 8 is going to give you a lot of practice on using that toolbox again. Use it to your advantage to review and just kind of get kinematics deep into your soul. We do need to kind of talk about a special type of motion that we can now really talk about, and that's rolling motion. Whenever we are talking about rolling motion in this class, we are referring to rolling without slipping. What kind of friction exists between the tire and the table right now?
Static.
It is static friction, okay? The tire and the surface are not moving relative to each other, okay? Whoops, they're moving in concert with each other, okay? And in rolling motion, right, assuming that there's no slipping, no drifting, Okay? The following things are true. Oh, it does. The wheels on the bus go round and round. Is that song still sung anywhere? Kinda. Yeah. Well, yeah, what's a bus? All right. So, let's say that this wheel is rotating. No, it's not. No, let's go this way. So if the wheel is rotating that way, is it moving left or right? Like if it's rolling along the ground, right? Which way is it going? To the right. Okay? One way to indicate that is to talk about the velocity of the center of mass. I put down COM because I don't want to confuse that with like centripetal velocity or something like that, right? Okay. We haven't talked about center of mass yet, but you all know what it is. Point to the center of mass of this wheel. It's right here in the center, right? Okay. So none of our wheels are going to be some weirdo center of mass offset or anything like that. All of our wheels are nice and symmetric, okay? So the center of mass is right here, and we'll do more about that next week in lab. But the speed, so does this wheel have omega? Yeah, because it's rotating, right? But it also has a linear speed that the center of mass is moving, okay? That center of mass speed, and again, sorry if this is a little bit confusing, actually turns out to be our omega. So if you know how fast the center of a wheel is moving, like if a car is going along at 10 meters per second, or 27 meters per second, which is 55 miles an hour, then you can calculate it's the angular speed of that tire if you know the tire's radius. But notice something. Angular speed is also tangential speed. As this wheel rolls along the ground, the points that are on this side of the wheel, which way are they going? Like, what's the tangential direction right here? It's up, isn't it? And what about on this side? Down. Up here? In the direction of travel. And down here? Opposite the direction of travel. So that means that on the wheel, this side is moving at V, this side is moving at V, the top is moving at 2V, and the bottom, because it's got tangential right there. So what do I mean that it's V, 2V, V, and 0? This is the vector sum of the tangential velocities that exist because of the rolling motion, the circular motion, plus the fact that this thing is also moving sideways. All points on this wheel, every piece of mass is moving in a line, isn't it? But it's also rotating. So as we look at like this speed over here, right, it's down but also moving sideways. So it's kind of the net is that direction, right? Over here the net's this or this way. Here we double up, right? Not only is it rotating, but it's also moving sideways. So the top of the tire is really going twice as fast, and the bottom,
Nothing at all.
it cancels. You have the tangential velocity from the rotation, but then you also have this, right? The rotation down here on the bottom is backwards compared to how fast the masses are moving sideways, and they cancel each other out, which is another reason why it's static friction. What's the speed of every tire on the surface of every road, assuming it's not skidding? 0, and that means static friction because the road itself is also 0. So that's just kind of the special case of rolling motion, and it allows us to make this assumption that the center of mass speed of the wheel is equal to r omega. With that being the case, we can now do any problem backwards and forwards in Latin or Greek. It doesn't matter. We can do it all. And really, okay, you have to make a decision. You can tackle all of these problems as if they're chapter 2 problems, and then at the end, kind of convert into the angular form. Or you can start in the angular version and just work it all out that way. The Google Translate equations will handle it all for you. For this example, just to review chapter 2 stuff, I'm going to do it in its linear form. And I kind of want to do it that way because look at these units. What have they given me? They've given me sort of linear things, right? So if they're linear, I'm going to go ahead and just see if I can't do as much as I can with the linear stuff and then convert that, right, into what they're asking for, right? So what are they asking for? They're asking for number of revolutions of tire. What's the symbol for number of revolutions of tire?
Omega?
Nope, that's velocity. No, that's time.
Theta?
Theta.
Oh.
Yeah, it's delta theta. I'm looking for part A, okay? I'm looking for delta theta, okay? What is the linear analog to theta? X. So really, if I can find X, I can then find theta. That's a plan, okay? Angular speed, what are they asking for in part B? Angular speed is omega, right? Okay. So what am I going to need to know in the linear version so I can convert it over? Velocity. If I can find my velocity, I can convert that into omega. So that's kind of my plan. I don't know why that second one was in blue. But that's what I'm going to try to do. So let's do part A. What do I know? Do I know the final speed? 22. Do I know the initial speed? 0. Do I know the acceleration? No. Do I know the time? Yes. Do I know how far it went? No. So what do I do? First equation has acceleration in it. Is there any of the, let's go back to this screen. Are there any equations up here that can get me the distance that I want without the acceleration? No. So what am I going to have to do first? I'm going to have to find acceleration first, and then I can figure out, okay, so which of these do I want to use for acceleration? Yeah, first one. It's right there. We know this, and time. We can find the acceleration. And then once we have that acceleration, how do we find x? We can use the third equation. Third equation would require algebra. Second equation, can second equation work? Yeah, I got all that stuff, and it's already algebraed for me. So I don't want to do algebra. So my plan is to use first for A, then second for delta x. So first one, whoops, v equals, well, see, it's the same. By the way, in my head, there are not two toolboxes. There's one toolbox, and I just write down either Greek or Latin, depending on, is it angular or linear? V equals V naught plus AT. Solve that for A. That's going to be V minus V naught all over T. Let's see, that's 22 divided by 9. I got 2.44, is that what you got? Meters per second squared. So now that I have that, delta x is equal to V naught T plus 1/2 AT squared. 0 plus 1/2, 2.44, 9 squared. I got 98.8 meters. Okay, so that's how far the car went in a line. So how do we find out how many revolutions the tire makes? Is there anything in our toolbox that could link a linear distance in meters to an angle in radians? The arc length equation. I can solve this for the angle if I know the arc length divided by the radius of the tire. What total linear distance, what total arc length did this tire travel? 98.8 meters. The arc length is equal to the distance the center mass of the tire went. So 98.8, and then this is very, very important. What do you divide by? 0.29. Good. Not 0.58. Because what's 58 centimeters? It's the diameter. How many times have I screwed that up?
Many.
All the time, right? I forget that diameter is not radius, right? It's 0.58 divided by 2, right? Is the radius of this wheel. So I did that and I got 340.7. Oh dear, what units would this be in? What are the units of arc length? Meters. What are the units of the radius? Meters. What's a meter divided by a meter? It's a radian. Because a radian is a nothing unit, right? So I know how many radians it was. They want what? Revolutions. So how do I get 340.7 radians into revolutions? There are 2 pi radians for every 1 revolution. And I got 54.2 revolutions. Notice, like, not only have we taught you Greek, but we're making you do chapter 1 and 2 simultaneously in a problem. Now, we kind of did that a little bit before, but it's definitely happening now, especially with some of the Google Translate equations that come along for the ride. All right, B. We want omega in revolutions per second. Well, do we know anything about V? Yeah, V is 22, isn't it? So how do I get from V to omega? Google Translate. It's R omega. So that means omega is going to be V over R. The V is 22. And the R, 0.58 divided by, was that 0.29? Yeah, it's 0.29. And that's meters. So this is going to end up in radians per second. And I got 75.9 radians per second, but they didn't ask for that. What did they ask for it in? Revolutions per second. So 75.9 radians per second. And for 2 pi radians, there's 1 revolution. Radians cancel. Revolutions per second is my answer. 12.1 revolutions per second. Do be careful with the units. What are the standard units for angular quantities? Radians, radians per second, radians per second squared. Those are the standard units and the ones you want to do calculations in. You'll need to convert before and after probably into more annoying units like revolutions per minute, revolutions per second. This is a very common thing that has to be done, whether you're in the metric or stupid unit system, but it's something that you have to do. Was there a hand out there?
Yeah. I was just going to ask, how did you find the radius?
The radius was given in that problem. It said that it was it 58 centimeters diameter of a circle. Chop it in half, that's the radius. That was the end of chapter 8. I'm literally out of slides. There's no more, right? So I've done it. You've got a lot on your plate, right? Chapter what is due on Saturday? 7. Chapter 8 is due next Saturday, but chapter 9, the biggie, is next week. Get chapter 7 done. Get chapter 8 done as fast as you can. Be ready for chapter 9. Try to work ahead if you can. If I don't see you in grasp, have a great weekend.